So the folding technique will be used to fold the given biquad filter, and the folding factor is 4. So this biquad filter is having 4 adders: adder number 1, adder 2, 3, and adder 4, and it is having 4 multiplier 5, 6, 7 and 8. So I have numbered the nodes. So node number 1, 2, 3, 4 is representing adders, and node number 5, 6, 7, 8 is representing multipliers, and folding factor is 4. So this means that the task of 4 adder will be performed by a single adder, and the task of 4 multipliers will be performed by a single multiplier. PA is equal to 1, PM is equal to 2. So this means that PA, that is the pipeline stage of adder. So this adder is having one internal delay. So this adder is one stage pipeline adder. PA is equal to 1, and PM is equal to 2. So this means that the multiplier is having two internal delays. So it is called two stage pipeline multiplier. PM is equal to 2. So since n is equal to 4, so one iteration will be completed in 4 clock cycles. Okay? Because one adder will perform the task of adder 1, 2, 3, 4, and one multiplier will perform the task of multiplier 5, 6, 7, 8. So this is the adder and multiplier that we have to use in our folded circuit. So this adder will perform the task of any adder, let's say 1, then it will perform the task of second adder, then third, and then fourth. So in each cycle it will complete the task of one adder. Okay, so just I have written this sequence in random. It is not necessary that the task will be executed in this sequence. Okay, similarly this multiplier will complete the task of any one multiplier, let's say it is 5. Then after that it will complete the task of second multiplier in second cycle, let's say it is 6. Then in next cycle, let's say 7, and then in the last cycle, let's say 8. Okay, again repeating, it is not necessary that the task will be executed in the sequence. Okay, so a iteration will have 4 cycles that can be represented by 4L plus 0, 4L plus 1, 4L plus 2, and 4L plus 3, in this manner, where L is the iteration number. Okay, so if L is 0, this term will be 0, and this will be 0, 1, 2, and 3. If L is 1, so this term is 4. So this is first iteration, first iteration, second iteration, L is 1, and it will be 4, 5, 6, 7. Okay, after that 8, 9, 10, 11, like this. This is second iteration, this is third iteration. So in each clock cycle, the this adder and multiplier will complete the task of any one of the adder present in the circuit. Okay, so this is the sequence. So we have to determine the sequence, that task of which adder will be executed in the first cycle, then next adder, then next, and then the last one. Similarly, we have to determine the sequence for multiplier also. So this sequence is known as folding sets. Okay, so set S1 and set S2. Set S1 belongs to adder and set S2 belongs to multiplier. So in the first cycle of an iteration, this adder will perform the computation corresponding to adder number 4. Then for second adder, this adder will perform the computation. Then for adder number 3, and then for 1, and same thing is applicable to multiplier. So in any iteration there will be 4 cycles as mentioned earlier: 4l plus 0, 4l plus 1, 4l plus 2, 4l plus 3, where l is iteration number. So this is the first cycle, second cycle, third cycle, fourth cycle. So in first cycle, the pipeline adder will execute the task corresponding to adder A4, then for A2, then for A3, and then for A1. Similarly, the two-stage pipeline multiplier will perform the task corresponding to multiplier M5, then M8, then M6, and then M7. So these sequence can be obtained by precedence constraint, but in this case it is given to you. Normally it will be given to you, otherwise you can determine it. So this information is also written over the computation unit. For example, for node 1, it belongs to set S1 and it will be executed in third cycle in the folded circuit. This belongs to set S1 and it will be executed in the first cycle in folded circuit. This is adder number 4 that belongs to S1 and it will be executed in the first cycle in folded architecture. Similarly for multiplier, set S2 comma 0. So it will be executed first in the folded circuit, after that multiplier number 8, then multiplier number 6, and then finally multiplier number 7. So this is the sequence. So based on these informations, now we have to write folding equation, because folding equation is the basis of this technique. Okay, so the folding equation is df u to v h e. This is given by n is folding factor, so in this case n is 4. W is the weight of h between u and v, so we can obtain this from the given graph. Pu will be equal to Pa if the node u is adder, and Pu will be equal to Pm if the node u is multiplier. So the value of Pa is 1 stage pipeline adder, and the value of Pm is 2 stage pipeline adder. And V and U can be determined from this sequence. Okay, so V and U can be determined from this sequence. So now we have to write the folding equations for each of the edges. So there are total 11 number of edges present in this graph. Okay, uh, so we have to write 11 folding equations. Okay, so let's start from node number 1. So df node number 1 to this is an edge. Okay, so it doesn't matter where there is an element present in between. Okay, we have to consider this as a edge, because if you will convert this form into a equivalent DFG form, so this D will serve as the weight of this edge. Okay, so df 1 to 2, n is 4, one delay element is present in between, so it is 1, and since this is adder, output will be generated from this adder and it is having one internal delay, so the output will be delayed by one cycle. Okay, and this is V. Okay, so V, this is V. This will be executed in the first cycle, and this is u. This will be executed in third cycle. Okay, so now since there is a delay element present in between, so this first cycle belongs to L plus 1th iteration, and this third cycle belongs to Lth iteration. Okay, so this is 4 minus 1 plus 1 minus 3. This is 1. So df 1 to 2 is 1. Okay, next is this is edge. So 1 is also connected to node 5, and there is a delay element in between. So df 1 to 5, n is 4, we is 1, pu is 1 for the same reason, plus this is 0, and this is 3 minus 3. So this is 0. Okay, so df 1 is also connected to node number 6. So df 1 to 6 with one delay element in between. So 4 1 minus this is pu is 1, value of v is 2, and value of u is 3. So this is 2. Okay, so writing one equation for multiplier, let's take node 5 and 3. So df 5 to 3 and 4, no delay element is there, so 0 minus, since this is a multiplier and it is 2 stage 5 times, so pu will be 2 plus value of v is 2 and value of u is 0. Okay, this is 4. So here you can see that there is no delay present in between. Okay, and this node depends on the result of node 5. So it is obvious that result generated by this multiplier will be consumed by this adder in the same iteration. So writing for 4 to 2 df 4 to 2, no delay element is in between, so 4 into 0. So this is adder, so value of pu will be 1. This is 1, value of v is 1, and value of u is 0. So this is 0. So here you can notice one thing, that if there is a delay element in between, so this value v value is less than u value, and if there is no delay element, for example 5 and 3, the value of v is 2 and u is 0. Okay, so v is greater than u. Second example, value of v is 1, u is 0. So if weight of h is greater than 0, v is less than u, and if weight of h is 0, v is greater than u. Okay, so there is a simple reason behind that. Okay, so considering this node 5 and 3, this node, that is adder, it cannot perform its computation till node number 5 completes its execution. So node number 5 will complete its execution, it will generate the result, and then node number 3 will use this result for further computation. Okay, so the result generated by this node will be consumed by node number 3 in the same iteration. Okay, so that's why node 5 will execute first and node 3 will execute afterwards. So that's why v is greater than u and v minus u is greater than 0. Okay, and considering this edge from 1 to 2 with one delay element, so the result generated by this node 1 will be consumed by 2 in the next iteration. So suppose it generates result in lth iteration and there is one delay element in between, so it will be consumed by node number 2 in l plus 1 iteration. Okay, these things are already discussed in previous lecture. Again, I am repeating this. Okay, so for w greater than 0, v can be less than u or it can also be greater than u. Okay, that depends. If we is 0, v will be always greater than u. Okay, so this graph contains 11 edges and I have written the folding equation for each edge, and I have also explained how to calculate this taking some of the edges. Okay, so based on these edges you have to draw the folded architecture. So the folded architecture consists of a one staged pipeline adder, a two staged pipeline multiplier with some delay elements, and the input provided to this adder and multiplier will be via multiplexers. Since the folded architectures are also known as time multiplex architectures, so input will be provided via multiplexers. So a iteration consists of 4 cycles. So I have drawn 4 switch at every input point. This is a 2 input adder, 2 input multiplier, and each input can be connected to any of these 4 switches. Okay, so for nth iteration during the first cycle, this point will be connected to switch number 0. In the first cycle it will be connected to then switch number 1, then in the next cycle it will be connected to 2, and then in the last cycle it will be connected to switch number 3. Then in the next iteration, that is l plus 1, this will be again connected to switch number 0, then 1, then 2 and 3. Okay, and the same applies for the remaining switches. So this is the given sequence. For adder it is 4 2 3 1, and for multiplier it is 5 8 6 7. So starting with adder, that is adder number 4. So adder number 4 is receiving its input from 2 nodes. Okay, from this graph you can see that this adder number 4 is receiving its input from node number 6 and node number 8, and you can also get this information from this folding equation. So 6 to 4, and this is 8 to 4, and 8 and 6 both are multipliers. So 8 and 6 are multiplier. So this means that during the zeroth cycle, this input will be received from the multiplier. Okay, so now you have to refer this equation number 9, that is 6 to 4 and 0. Okay, so this is saying that 0 delay element is required between 6 to 4. Okay, so the output of the multiplier can be directly connected to switch number 0. Okay, so I am connecting this is the output of the multiplier. Okay, and I am connecting this to switch number 0 because adder number 4 will be executed in the 0th cycle. So this is for 6 to 4. So in the 0th cycle, this adder has received one input, and second input will be received from node number 8, that is also multiplier. Okay, and df8 to 4 is one delay element. Okay, so the output of the multiplier should be delayed by one cycle, so one delay element, and then connect this to the switch number 0 of second input. This is how we have to make the connections. So after that, this adder will perform the task of adder number 2. Okay, so considering adder 2 is getting input from node 1, and second input is from node 4. So 1 and 4 both are adders, so output of adder will be connected to its own input. Okay, so how many delay elements are required, that is already calculated here. So 1 to 2, one delay element. So this is the output of adder, and one external delay is required, so I have already drawn some delays. So one delay element, and output of this adder should be connected to switch number 1, because now the adder will execute the task of adder 2 in the first cycle of an iteration. And second is 4 to 2. 4 to 2, zero delay element is required, so no external delays no external delay is required, so directly connecting this to switch number 1 of the second input. So in the similar manner you can do all the connections. Okay, so now for adder number 3, adder 3 is receiving input from node 5, which is a multiplier, and node 7 node 7 is also a multiplier. So 5 to 3, zero delay. Okay, so you can directly connect this point, no external delay, output of multiplier connected to switch number 2, and 7 to 3, one delay, so output of the multiplier delayed by 1. I have already drawn this, so connect this to switch number 2. So then connect this to switch number 2, and last adder 1, it is getting input from output signal and node 3. Okay, so node 3 to 1, you have to refer the equation df3 to 1 and value 0, and node number 3 is adder, so this is 3, this is input source. So 3 to 1 output of adder without any external delay. Okay, so this is the point. The connection is already there, just you have to extend the wire. And this second input is from external source, so at this point you can give the external signal. So in the same manner you have to connect the inputs of multiplier. So you can see that the one input to all the multiplier is a constant value. This is A, B, C and D, and the sequence is this multiplier will execute first. So first A will be given to switch number 0. After that D, then B, and then at last C. So this is the order in which the constants should be given to this input A, D, B and C. Okay. Now we have to connect the second input. So starting from multiplier 5. So multiplier 5 is getting input from node number 1, which is an adder, and 1 to 5 is 0. Okay, so output of adder with 0 delay. So this is the output of adder with 0 delay that should be connected to the switch number 0. Next is multiplier 8, and it is also getting input from node 1, and 5 delay elements should be in between. Okay, so I have to so I have already drawn delay elements, so total number, so 1 2 3 4 5 5 delay elements, and output of this should be connected to switch number 1. Okay, that's why I have drawn 5 delays at this point, maximum 5. Next is multiplier 6, and input is again from node 1, that is adder, and delay element required is 2. So 2 delay elements. Output of this should be connected to switch number 2, and last is 7. Okay, so here I have missed one equation. df 1 to 7 is 4 into 1. One delay element is present between 1 to 7, minus 1 plus 3 minus 3, and this is equal to 3. Okay, so 1 to 7 it is getting input from adder 1, and 3 delays should be in between. So 3 delays, 1 2 3. This output should be connected to switch 3. So connecting switch 3 with this output. Okay, so this is the final folded structure. Okay, so the output is from node number 2, that is adder, and this is performing its execution in cycle 1. So the first cycle it will complete its execution and the result will be available in the next cycle, that is in the cycle number 2. So the output should be taken from the output of adder and it should be sampled in the second cycle. Okay, because in the first cycle get the result is being generated and the next cycle it will be available, so output should be sampled in second cycle. So consider this biquad filter, and suppose now we want to fold this by a factor 4 and PA is 1, PM is 2, so all the information is same, just so this filter that we have solved now, and this filter is same except that delays are placed at different position. Okay, rest all the information is same. So now suppose that I want to fold this architecture, so I have to write the folding equations using the same formula. df u to v is given by n into w minus pu plus v minus u. So pu is 1 if node u is adder and pu is 2 if node u is a multiplier. N is 4, w is of w e is the weight of h between u and v, and v and u are v and u can be taken from this information. So 11 edges are there and for each edge we have to write the folding equation. Okay, so df 1 to 2, so 1 to 2, no delay element is in between. Since this is an adder, so p will be minus 1 and value of v will be 1 and u will be 3, so 1 minus 3, so this is minus 3. And for 1 to 5, this is 1 to 5 with one delay element in between, so 4 into 1 minus 1 plus 0, this is v, and 3, this is u, so 0 minus 3, this is 0. df 1 to 6, 1 to 6, this is 1 to 6 with one delay element, so 4 into 1 minus 1 plus v minus u, so v is 2 and u is 3. So in the same way you can write equation for all the edges. So 11 sets of equations is there, and you can see that this is negative, this is negative, this equation is negative, and this is negative. So 4 negative values. And what does this signifies? This means that the folded architecture from 1 to 2 there should be a delay of minus 3. From 6 to 4 there should be a delay of minus 4 in the folded architecture, and this is delay of minus 3 and minus 3. But this is impossible. Delay is a physical quantity which cannot be negative. Okay, it can be 0 or 1 or 2 some integer values, but it cannot be negative. So the condition is that df u to v e should be greater than or equal to 0. This is the condition. Okay, so based on this condition, df is given by n of we minus pu plus v minus u. This should be greater than or equal to 0, but we have negative values for this graph. So does it mean that we cannot fold this architecture? Okay, so we can fold this architecture, but what we have to do, we have to retime it. We have to do retiming before folding. Okay, so by doing this, the place the delay elements will change their place, and we have to do retiming in such a way that this condition holds. Okay, so we have to, now this is the constraint before doing retiming. Df u2 ve should be greater than equal to 0. This means that n of we minus pu plus v minus u should be greater than equal to 0. Okay, so let wr is the weight of all the edges after retiming. Okay, and this condition should hold. So n times wr minus pu plus v minus u should be greater than equal to 0, and wr is given by we plus rv minus ru. Okay, so pu plus v minus u, this should be greater than equal to 0, and n times we minus pu plus v minus u plus rv minus ru, this should be greater than equal to 0. So this thing is df u to v e, the same thing, and so this will be multiplied by n because of this, plus n times rv minus ru should be greater than equal to 0. So rearranging this equation, ru minus rv, taking this term to the right hand side and rearranging the equation, this gives ru minus rv should be less than or equal to df u2 divided by n. So you have to maintain this condition while doing retiming. Retiming is basically calculation of these values ru and rv. So if rv and rv is calculated in this way, this condition will always hold true, and we will get positive values. So for positive values or 0, we can easily do folding. So we have to retime this. Okay, so the retiming equation following the folding constraints can be derived from this folding equation. You have to divide this by n, 4 in this case, and you have to take the floor value, for example this. So minus 3 by 4 will give you minus 0.7. Okay, integer smaller than this value is minus 1, so minus 1. 0 by 4 is 0, 2 by 4 gives you 0.5. The integer smaller than this is 0, so 0 value. 7 by 4 gives you 1 point something, and you have to take 1. So 5 by 4 is again 1 point something, and you have to take 1. For 0, the value will be 0. For minus 4 divided by 4 gives you minus 1. Minus 3 by 4 gives you minus 1, and minus 3 by 4 gives you minus 1. Okay, so you have total 11 sets of inequalities, and I have already discussed how to solve this. Okay. First you have to draw the constraints graph using these sets of inequalities, and if no negative cycle exists in that constraints graph, you can apply shortest path algorithm. For example, Bellman-Ford, Floyd-Warshall, and then you can solve for R1, R2, and R3, R4, R5, R6, R7, and R8, and then you can calculate WR. WR is given by WE plus RV minus RU, and then you can perform folding. Okay, so if you will retime this graph, the retime graph will be this one. Okay, so by performing retiming using these sets of equation, okay, I am not solving this, you can solve this, you will get this retime graph, and the folding process of this graph is already discussed.